Hello everyone and welcome to a new Sega Mega Drive Genesis game dev tutorial. In the coming weeks we're going to start to explore some more complex computer programming topics such as level collision and so on, and before we do that I want to do a quick lesson to go over some different data types, for example 8-bit, 16 and even 32-bit numbers. For anyone who was playing games in the 90s, you'll probably remember that the subject of bits and how many bits a certain console had or did not have was a very hot topic. After watching this lesson, I hope that everyone has a better idea of what bits are and how they affect how you program the games. As always with these tutorials, my focus will be on the practical applications of this knowledge, but for those of you who are interested in digging deeper and looking at the computer science side of things, I will include some links below so you can do some further reading. Okay, let's get to it. During the lesson so far, we've used different data types in our variables. For example, use an integer when we write int, and we've also used, I think, u16 before too. So now we're going to delve a bit deeper into what these are, and let's start with 8-bit numbers. We'll start by cleaning up our template project to begin with, so get rid of that, and then we can change the text here because we want to remind ourselves what's been written on the screen. So if you remember, when you draw the text, these last two numbers that you put into the function determines which tile they're put at. So if we do 0, 0, it should be in the top left hand corner, and we'll change the text to 8-bit number. So to use an 8-bit number, we're going to type U8 and then a space, and then we're going to put the name of the variable we want to write. So if you notice here, if I want to write it as 8-bit something something, you can't begin in C language, you can't begin a variable with a number. So we can change it here and go number underscore 8-bit, and then we make it equal to 0, and of course don't forget the semicolon at the end. We're now going to print this variable on the screen, and this sounds very simple, but in C language it's a bit more complicated than in newer languages, because if you give C a number, it doesn't know whether it's a part of a number that it needs to calculate or whether it's a piece of text that it needs to print on the screen. So you have to really tell it, whereas I understand that in newer programming languages it's a lot easier to do. You can do it in maybe one line of code, but we're going to need a few lines of code to do this. In order to do that, the first step is to create what's called a string. So we start off with this char. Now this is short for character, so it's going to let then C language, the compiler knows it's going to be some text. Then just as with other variables, you can just call it whatever you like. I'm going to call it text underscore 8-bit, and now we have to open these square brackets, and inside we have to tell it how many characters, how many letters or numbers is going to be in this piece of text. And we're going to do it as 3, so I can fit 3 different numbers, so up to 999, and then we're going to do a semicolon. Before we can print the number, the variable, to the screen, we need to first transfer the number from the variable into that string we just created. So in order to do that, we're going to use this function here, sprintf. This function requires 3 pieces of information. So the first piece of information we're going to give it is our string, the name of the string we created. So we can simply paste that into the first brackets here. Next, we have to tell C what kind of data we want it to print and how long that data is in terms of characters. Now, this can get a bit confusing if you never studied C before, and the syntax is a bit ugly, but so I'm displaying now on a different formats you can use. Just so that you know, for this lesson, we're going to be using the %I symbol here. When we input this information, we're going to need to add these quotation marks first, and then we're going to put the percentage, and then the next is a number of how big the string we created is. Remember, we did it as 3, and then we're going to type the I and then another comma, and we're going to put in the third piece of information, which is the variable we want to convert to text. The final step is to tell SGDK to display the variable on the screen. So we're going to use this function here, vdp underscore draw text bg. And if you open the brackets, the first piece of information it's asking for is the background plane you want to display the text on, and we're going to choose bg underscore a, which is the foreground. After that, you need to type the name of the string we created, where we put the chr, so that'll be text underscore 8-bit and another bracket. And then finally, we're going to let it know where the tiles where we're going to display it on the screen. So we're going to do x coordinates, like the 0, and 1 for the y coordinates, so it appears just below where we've written 8-bit number before. Okay, we are done here. So just before I save, compile and run it, I'm just going to take you through the code through once more, because as I said before, is the syntax is a bit very ugly in C here, and it's not very human friendly, and newer programming languages, they make it a lot easier to do. But we're going to define the variable as normal, so you've done that lots of times before. We need to create a string, and then we need to use these 2 functions here to actually display the text. The first one sprints printf is to transfer the variable to the correct format, to a text format, and finally vdp draw text bg is actually display the text in SGDK. And as we run it here and compile, you can see that we have it on the screen and everything's working fine. In this particular lesson, I'm putting the variables on the screen to see how they update, just to teach you the differences between different data types. But actually, you may have seen from my Symphony of the Night development videos that I often put some numbers on the screen of different variables. This is a good way to do some quick debugging to see what's going on in the code, and especially if you have a problem or you just want to make sure everything's okay or you're just curious, it's a good way. I use this quite a lot just to keep an eye on what the code's doing and make sure everything's working as I expect it to work. Let's start to investigate these numbers now and see how high we can get this 8-bit number. So we've done this kind of thing before where I just add 1 per cycle, and you can add 2 or 3 per cycle if you want to. So let's do it using this syntax. If we're just adding 1 per cycle, we can use this plus plus, or you can do this plus equals 1. They're both the same, so use whichever one you prefer. If we're going to do higher than plus 1, we need to do plus equals 2, plus equals 3, and so on. If I now save and compile and run, you'll see that the number's constantly going up, so it's constantly changing all the time. And the highest number, as I'm sure some of you already know, is 255. As I stated at the beginning of the video, I'm going to include links for those of you who want to get a bit more involved in the computer science side of things. But just to have a recap here, just a quick summary. All numbers are made up of information. Computers are made up of bits, so 1 or zeros, and 8-bit numbers have 8 1 or zeros, and any combination of these, if you add all the different combinations up, you have 256 possible combinations. So if we want to represent numbers, then we can represent numbers from 0 to 255 and everything in between. Or if we're going to include negative numbers, it'll be minus 128 to 127. As soon as we go up to 16-bit numbers, that number increases exponentially, and we get up to 65,535 if we're not including any negative numbers. That number might be quite familiar to you because it's also the amount of both work RAM and VRAM the Mega Drive has. If you cast your eyes to the bottom of the screen, you'll notice we have some 32-bit numbers. Now, these are absolutely huge. We've already got the negative numbers included here, and even when doing that, the maximum number, positive number, would be 2,147,483,647. You might be wondering how the Mega Drive can use 32-bit numbers when it's technically a 16-bit system, although in some ways the CPU could be considered to be 32-bit. Now, obviously, if you think about the 8-bit systems, they would need numbers higher than 255, despite having an 8-bit CPU like the Master System and the NES, but they could use 16-bit numbers, for example. They just have to split up the number in 2, and obviously they probably can't process the information as quickly as with an 8-bit number, so they could use it, and the same applies for the Mega Drive with 32-bit numbers too. Okay, before we look at 16 32-bit numbers and also numbers with decimal places, let's quickly go back to the 8-bit number, and if you change the U8 to S8, it becomes a variable which can also display negative numbers. So if we save and run and compile now, you'll see that it only goes up to half the amount, and then it goes to, whoops, there's a slight mistake here. Let me go back to the code and see what's wrong. I'm sure there's something simple here, and okay, I worked it out. So what we need to do is we need to change the string so it contains 4 characters, because as well as displaying the 3 characters of the number itself, we also need to include the negative sign as well to reference a negative number. So you can see now we've changed those both to 4 rather than 3, and it's displaying correctly. So it's only going up to a max of 128 before falling back to minus 127. I normally don't have to use negative numbers in my code, but in case you do, then you know how to do it now. Skipping ahead a bit here, you see I've done the same for the 16-bit number. Instead, we're incrementing by 100s rather than 1, because otherwise we'll be waiting too long to see where it reaches its limit and where it rolls over. Also note that I had to make the string bigger here. I had to make it 6 rather than 4 to make sure it can hold all the numbers we need for the 16-bit number, and as it goes up and up here, if it reaches around 65,000, it should roll back to 0, and it has done so. It always goes back to the beginning, it starts counting from the beginning again. Just like we changed the 8-bit variable from U8 to S8 in order to include negative values, we can do the same here. So we can change it from U16, which only includes positive values, to S16. And then if we save and recompile, we should go up to half as much before returning to the negative. And you should see now it's all working fine. It goes up to half as much as before returning to the opposite negative number before rising again. Before we talk about decimal numbers, which is very important in our code, I just did the same for a 32-bit number too, the int. So you don't need to do, U32 or S32. Just if you use the int, the int that we've been using in previous lessons, that uses the 32-bit number, and as you can see, is a absolutely huge number. So this will definitely be sufficient for any of our purposes. I actually calculated that if we were to increment by 1 per cycle, it'd actually take I think it's 400 days, so over a year, until we got to the upper limit of 2 billion or so. To speed things up, every cycle it increments by 1 million. So we should reach the limit very soon here, and here we go, we're back to the negative numbers. So 32-bit numbers are really huge. At the end of the lesson, we're going to talk a bit about where you should use 8-bit numbers, where you should use 16-bit numbers, and where you need to use 32-bit numbers. However, before we do that, let's see how you use decimal numbers in your code. I'm sure you remember from previous lessons that we can't just do, for example, int x equals 1.5 or 1.1 or 1.2, and we can't do the same for U8 or U16 either, so we have to use a special data type. Let's start with a 16-bit decimal number, so we're going to have to do the type as fix16 and then give it any name you want. So I'm going to call this fix16 underscore number, but the name is something you choose yourself. And we also have to write now in capital letters fix16, open the brackets, and then inside the brackets you have to put the number you want to assign to the variable. I'll just skip ahead here as we go through the same process as before. We create the string, and I've made it quite big here, 10, which is more than enough to contain the number we need. Don't forget that we have fix16 number plus equals. We have to include the fix16 in capital letters and put a number in the brackets. And we also do this extra thing here in sprintf, where we have to type fix16 to int and then open brackets and then put a number inside those brackets. Otherwise it'll create some problems for us. So remember, you have to do that with all these 16-bit decimal numbers. So if we add 1 each time here, we can see that it keeps going up and up and up until it reaches this number here. So you can see it's just over 500 rather than over 65,000 as before. Now the reason for that is it still has 16 bits to represent the information, but it only can use 10 of those bits for the whole number, and it's using 6 of those bits to specify what the decimal point is. So instead of using 16 whole bits for the whole number, which gives it over 65,000 possibilities, in this one it only uses 10 to specify the whole number, which is a much lower number of possibilities, and the remaining 6 to represent the decimal point. Of course, the whole point of using these fix16 instead of U16 or S16 is so we can use decimal points. So instead of the usual adding 1, we can add, for example, 0.1. These kind of more slow ones are especially small numbers, especially good if you want to, for example, you want to scroll some clouds at a very slow rate, because 1 pixel per cycle is 60 per second, which may make the clouds move too fast. So often with clouds or other things, you might want to make a move a lot slower. The smallest number you can increment using the fix16 data type is 0.0157. I know it seems like a very particular number. I will include some information in the video description where you can watch some videos that explain the computer science behind it. I don't want to get into it in this video, but you can see here it's moving a lot more slowly, and if you need it to move even slower than that, or if you need to have a fixed decimal place number that can go over 500 or 1000 whole numbers, then we're going to need another one. We're going to use a 32-bit number, and that is fix32. Okay, so let's quickly do the same for a fix32 number. So I'm just going to copy and paste this here and make all the changes as needed. So change the text as 32, change the y coordinates where the text is going to appear so it doesn't cover over anything we've done it before, change it to fix32, change the name of our variable. We have to change this capital as well, so fix32 brackets the number you want to assign, change the name of the string to, and we're going to do the same in the while loop. So sprintf, we're going to make sure that it's transferring the correct variable to the correct string. We need to, again, before we had fix32 to integer to int, we're going to change that fix32 to int, and again let's make all the other changes too so it all fits. As I mentioned before, using fix32 instead of fix16 means we have many more bits with which to 32 bits to represent both the decimal places as well as the whole numbers. So both can be much larger. The whole numbers can be much larger and the decimal points can be much smaller. So we're doing it as 0.001 here, which is probably smaller than you'll ever need, but I'll just do it as a demonstration so we can see the fix16 number go up, albeit very slowly, and the fix32 will be going up even more slowly than that. So you'll keep adding 0.001 until we eventually, here we go, we get to a whole number and it finally adds that, and eventually go up to 2 and so on. So the biggest reason you would need to use fix32 instead of fix16 is with mostly is not to do with how small you can increment, because normally fix16 is enough for that. Even 0.1 is enough for most purposes. It's mostly for the whole numbers. So as we said before, fix16 only goes up to either just over 500 or over 1000, depending if you include negative numbers or not, whereas fix32 can go much higher. So if you think about when we were doing the big game maps before, they're normally wider or longer or higher than 500 or 1000 pixels, and if you use fix16, it's going to, as soon as you get over 500 or 1000, it's going to go back to the very beginning and you're going to get all sorts of weird behavior. So fix32 is definitely what you need to use for player movement. So anything you're recording where the player is on the map or where the enemy is on the map, you're mostly going to use fix32, and fix32 obviously is better than using an int, because the int only has whole numbers, whereas fix32 you can use decimal points. So you can include things like gravity and jumping, or you can even just make them, instead of having to make them move either 1 pixel per cycle or 2 or 3, they can move 1.2 or 1.5. So we're going to be using in the future, when we do the lessons on the cameras and other lessons for character movement, for player movement, we're going to be using the fix32 data type. I normally find the fix16 data type most useful for if you want to do any kind of slow scrolling. For example, the moon here has to scrolling quite slowly, and normally fix16 is enough for that. You don't need to go to fix32. Of course, you always want to use the smallest data type you can. So any 32-bit number takes up 4 bytes. Any 16-bit number is 2 bytes, and any 8-bit number is 1 byte. So you want to use the lowest one you possibly can. And when it comes to scrolling, I think any kind of scrolling, normally fix16 is enough. Whenever you want to do any super slow movement, you have to bear in mind the resolution of the screen. So for example, it's only in regular H40 mode, it's only 320 pixels wide. So the any object can only move across the screen at 1 pixel at a time. It can't move by half a pixel or 0.1 of a pixel. You can only move 1 pixel at a time. So if you do it less than 1, the scrolling, then it's going to wait until it gets to a whole number, keep adding up until it gets to a whole number, then it's going to shift, then keep adding the decimals until it gets to a whole number again and shift and so on. So if you make it too slow, it can end up looking a bit jerky, so you have to be careful with that. So as I said before, it's generally a good idea to use fix32 variables when it comes to player movement or enemy movement on a large map. Fix16 is normally sufficient for scrolling, and when it comes to 8-bit data types, 8-bit variables, what's that good for? Well, I think things such as, for example, player continues, because most games you get maybe 1 or 2 continues or 3 continues, so 255 is more than enough for that. You also have other things, for example, player lives, or, because normally you don't have, maybe the lives top up at 99 or even 10, it's not going to go up to 255. Maybe number of levels can be an 8-bit number. Or you can have, for example, someone gets hurt, either an enemy or yourself, you have the invincibility framed counter. So how long will you be invincible for before you can get hurt again, before you can get hit again and lose more life? Now normally that's maybe 1 second or half a second, so 255 would be over 4 seconds, which is more than enough. You can see where 8-bit numbers have been used in many games. For example, Legend of Zelda here, the number of rupees you have tops up at 255, but even some 32-bit console games use 8-bit numbers. For example, Final Fantasy VII here, lots of the stats will top out at 255. If there's anything you didn't quite get today, don't worry, we'll be going through lots of examples in future lessons. We're going to be using all these different data types, so as we use them in different situations, you'll get to learn when to use them and when not. I'm going to put a playlist linked in the video description below where you can learn more about how binary works, and especially how the fixed point binary fractions work, which is what we've been using today, and also how it compares to floating point binary fractions. Now, floating point, I think the first console to use floating point numbers was the N64, but you can learn the differences between those. I think it's quite fun to learn. Okay, so I think that just about wraps things up for this video. Thank you so much for watching. If you're interested in this kind of content, then please subscribe to the channel.
I'm interested in this.
And if you want to support the channel further, I have a Patreon account.
You won't go unrewarded.
And until next time,
Farewell.